The first part of chapter R.5 asks us to take a look at equivalent expressions. So what we're going to do is we're going to use substitution values for x in order to see which, if any, of these expressions are equivalent. The first one says x plus 2x, the second one says 3x, and the last one says 8x minus x. So here, if x were negative 2, we would have negative 2 plus the quantity 2 times negative 2, which would be negative 2 minus 4, which would be negative 6. So that value would be, well, let's do that in a different color. That value would be negative 6. Let's try that with 3x. So if I have 3 times negative 2, well, 3 times 2 is 6, and a positive times a negative is a negative, so that one is also negative 6. And with our third expression says 8 times negative 2 minus a negative 2. So that would be negative 16 plus 2, and that is a negative 14. So as you can see, the first two expressions both gave us negative 6. The second one gave us a negative 14. Let's try it with 5. If we use 5, then 5 plus 2 times 5 is 15. And 3 times 5 is also 15. And let's see, 8 times 5 minus 5 is 40, minus 5, well, that's 35. And finally, 0 plus 0 is 0. 3 times 0 is also 0. And 0 times 0 is 0. I'm sorry, 0 minus 0 is 0. So notice that even though at 0 all three expressions had the same value, only in the previous two did the first two expressions have the same value. So we can deduce from this, we can see that the evidence shows that the quantity 2x plus, well, x plus 2, let's write it the way it's written there. The quantity x plus 2x appears to be equivalent with the quantity 3x. And that bears out, right? If I have 2 of something and then I get one more of that thing, let's say they are cherries. Well, let's say they're white cherries. If I have 2 cherries and then I add to it a third cherry, then I have 3 cherries, right? Makes sense? Okay. So that's equivalent expressions. So the key concept here is equivalence, that x plus 2x's is 3x. Now let's define some laws that affect equivalence. When we make an equivalent statement, we're saying that whatever's on the left side of the equal sign is exactly the same as whatever's on the right side. So in order to maintain this equivalence, suppose I wanted to add 7 to this side of the equation. Well, now I'm out of balance, because if I add 7 over here, then I have 3x plus 7. Notice that we'll go ahead and put these two together, and it'll say 3x, and I'm adding 7 to it. If I haven't done so over here, then I no longer have a valid equality. So what do we have to do, in other words, to get that equality? And in order to do that, we need to add 7 over here. So whatever I do to one side of the equation, another way of saying that, I have to do to the other side of the equation. That seems to make sense. Let's take a look at another example. If I have x plus 3 and I set it equal to a number, 4. Well, now that I have only one x on this side, it should be pretty easy for me to figure out what x needs to be in order for that number plus 3 to be 4. You could probably do that in your head and intuitively know that x needs to be 1 in order for x plus 3 to be 4. But what's the algebra that supports that? Well, the first rule to maintain equivalence when we're manipulating one side or the other of an equation is we're going to use the addition principle. The addition principle is what your book calls it. All it means is whether I'm adding or subtracting by adding a negative number to one side of an equality. Here I'm going to add a negative 3. I also have to do that to the other side of the equality in order to maintain that balance. And so we do that, we add the negative 3 here because 3 plus a negative 3 is a number plus its additive inverse. And what happens when we add inverses together? We get the identity, which is 0. This now says specifically x plus 0 is equal to 4 minus 3, which is 1. And because 0 is the identity, we don't really need to write it. We don't really need to write the identity, so we can just say it's x is equal to 1. So the effect of adding the inverse, it cancels my 3's on this side. I don't have 3's anymore over here. And then I'm left with 1 on this side. So that's the addition principle. Let's see what would happen if instead of having x plus 3, we had 3 times x, and we set that equal to 4. Well, here's our equality. And remember that in order to manipulate, our goal in solving is to get x all by itself, to have one and only one x on one side of the equation, and on the other side having either a number, an integer, a fraction, or some other expression in this case. In this case, we will have probably, it looks like a rational number. Now, since this has 3 times x, we will use what your book calls the multiplication principle. And the multiplication principle works essentially like the addition principle. We add the opposite in the addition principle in order to get the identity. We add the inverse, the additive inverse. So now, instead of adding the opposite or adding the inverse, we are going to multiply the multiplicative inverse, or in this case, the reciprocal. So 3 is essentially saying 3 over 1. So the inverse of that would be 1 over 3. And then I can multiply this side by 1 over 3. One way to look at it, if you don't want to look at it as multiplying the inverse, is you can say, well, I can also just divide by the number being multiplied by x. Because when I do that, I have a number over itself, and anytime I have a number over itself, I have the value 1. So if I wanted 1 and only 1x, I have that by putting 3x over 3. And of course, to this side, I have to do the same thing. That's how I maintain the balance. So 1x, or just x, remember, we don't need to write that x because it's the identity. That's why we put it there. X is equal to 4 divided by 3, or 4 thirds. So that's the multiplication principle, and the addition principle, and maintaining equivalence on your expressions.